Good evening, everyone. Just making sure that our recording is in fact working. Looks like it. It looks like it, although I don't see it on our actual YouTube channel. If there is anyone online who would chat something, let me know that you're there. Start broadcasting with multiple regression. Oh, what does it say? 621. No one caught me on this before that I put the wrong course number for all of your
I was just wondering
online lectures. This is definitely not a topic in BIOS 621. This is the topic for your class. But I just, and we are doing multiple regression today. But for some reason, our YouTube stream is not working.
Because there's one viewer.
Right, I guess that's
me, actually.
Oh,
Yeah,
What's that?
that's me.
You.
Yeah, I'm trying to.
Can you see anything, or does it
Yeah,
say
now-
live stream is
now-
starting soon?
Yeah, it's now I can see.
You can see the.
Yeah.
Okay. Well,
Yes.
okay. If you can see it, then I'm going to quit and assume that it's working. Thank you. Would you mind just taking a look now and then to see if anyone has asked a question? Okay. So this is our last lecture of the semester, and we're going to cover multiple regression. Something that you will be doing plenty of during your time as an MPH student here in the BIOS stream. This is just the start of it. So your textbook has a nice chapter on this, and much of this lecture is based on that chapter. And so if there's anything, if you want more information, please do take a look at the textbook. I'm going to start with a review of some of the different bivariate methods that we've covered, and then go into regression for more than 2 variables, including reading the tables of output, collinearity, and this thing called adjusted R-squared. So to review, we've covered a number of different bivariate methods and categorized them by what the types of variables are. So we are referring often to one variable as the response and outcome variable and another one as the predictor. Even when we don't know what the causality of the two is, it does matter for the purposes of inference. In some cases it doesn't matter, like the chi-squared test. When we have 2 categorical variables and you use the chi-squared test, we covered a couple of other options as well. It really doesn't matter which one is the dependent and which one is the independent variable. You can draw contingency tables, just the tables of the frequency of all combinations of counts. And we covered how to calculate the expected values, chi-squared statistic, and use the chi-squared distribution with a number of degrees of freedom that you should be able to calculate for any size table, to do a hypothesis test. And in the case of just a binary response variable, you can also do logistic regression, something that we don't get into this semester, but you'll do plenty of in BIOS 1 next semester. When the response variables is continuous and the predictor is categorical, you can use a t-test, or you can use analysis of variance, which looks at differences in the amounts of variance explained by the groups and by residual variance. And side-by-side box plots or bar plots to visualize these type of data. And then last class we covered the case of two continuous variables and covered scatterplots, linear regression, and Pearson's correlation. And last class we covered the case of two continuous variables and covered scatterplots, linear regression, and Pearson's correlation. And last class we covered the case of two continuous variables and covered scatterplots, linear regression, and Pearson's correlation. And last class we covered the case of two continuous variables and covered scatterplots, linear regression, and Pearson's correlation. And last class we covered the case of two continuous variables and covered scatterplots, linear regression, and Pearson's correlation. And last class we covered the case of two continuous variables and covered scatterplots, linear regression, and Pearson's correlation. And last class we covered the case of two continuous variables and covered scatterplots, linear regression, and Pearson's correlation. And last class we covered the case of two continuous variables and covered scatterplots, linear regression, and Pearson's correlation. And last class we covered the case of two continuous variables and covered scatterplots, linear regression, and Pearson's correlation. And last class we covered the case of two continuous variables and covered scatterplots, linear regression, and Pearson's correlation. And last class we covered the case of two continuous variables and covered scatterplots, linear regression, and Pearson's correlation. And last class we covered the case of two continuous variables and covered scatterplots, linear regression, and Pearson's correlation. And last class we covered the case of two continuous variables and covered scatterplots, linear regression, and Pearson's correlation. And last class we covered the case of two continuous variables and covered scatterplots, linear regression, and Pearson's correlation.
There must be something feeding back up there. Or maybe it could be somebody online's got their speaker on or something. Or has, it's not.
No, we
muted.
shouldn't be getting
Yeah,
sound back
they
from
should
anyone
have
online.
everybody muted, yeah.
It
Must be
stopped
here.
here too.
What's that?
What's,
We were hearing here too, but it's now stopped when you close down the YouTube.
I see. It's just a bit of delay. Okay, it's gone now.
it's okay now.
Okay. More or less. I have the volume turned off here, so I don't know what's coming through. Anyways, so yeah, first one is wonky. What does that mean anyways, predicting accurately? I mean, each one is predicted to varying degrees of accuracy. None of them are an exact prediction, but you don't have to make an exact prediction to be accurate, right? So anyways, let's put a big, no. Okay, books that are 10 cubic centimeters over average are expected to weigh 7 grams over average. What do you think?
Maybe true.
What's that?
Yeah, true. Maybe true.
Yeah, true. And it doesn't really matter that it's over average over any particular weight. If the slope here of 0.7 is telling us that for a 10 cubic centimeter increase in volume, you expect a 7 gram increase in weight. It doesn't matter whether it's over average or over 200 or over 1400 or whatever. That's the slope. So this one is okay. The third one, the correlation between weight and volume is R equals 0.80 squared, which is supposedly 0.64. The correlation, Pearson correlation.
You square it to get the Pearson correlation?
Yeah, no, this is wrong. This should be
0.0064.
It should be the square root. Square root of 0.8. Does anyone know quickly offhand what the square root of 0.8 is?
.9 or something.
Yeah, it's going to be something more than 0.8. It's going to be It's going to be pretty close to 0.9. Just under 0.9, like maybe 0.895 or something.
0.89.
89, okay. 0.89. And we should really call that lowercase r. That's what we usually call Pearson's correlation. I gotta get in the habit of bringing in my little tablet, Tony, like you have.
If you want to borrow it, you can. I think I have it with me.
Yeah?
Sure.
Yeah, I might plug it in. That would help for some of these things. Okay, last one. The model underestimates the weight of a book, the weight of the book with the highest volume. So which one is that? This one?
Overestimates
Is that true? It overestimates it, so that's wrong.
Oh, and there's still my luggage
Okay,
here with me. Not here.
that's all right. Okay. It's a little hard for me to type, but it overestimates that one. Okay, no problem. This is just your regression table outputs. This is what I did in R. You get something very similar looking in SPSS, but there it is with your slope of 0.7 and your intercept of 107 with the additional columns for your standard error, a t-value, and a p-value from the t distribution. And this uses a t distribution because both of these can be considered averages on a sampling distribution. So anytime you do linear regression, your coefficients in a linear regression, whether it's standard simple linear regression or multiple regression. If it's just a simple linear regression, where it's y equals some things, whether those predictors are continuous or categorical, as we'll see, your estimates will be t-distributed. We get a few other things here. This residual standard error. Those are the sum of the squares of residuals, the degrees of freedom, multiple r squared. We don't know what that means yet. And an adjusted r squared, which is a little bit less than that, and a few other things. This F statistic for an analysis of variance. Okay, but let's learn what some more of those things look like. And it'll make more sense to use them once we consider the type of book, whether it's hardcover or paperback. So just using a couple different symbols here and colors, you see that the hardcover books tend to be on the upper half and the softcover books tend to be on the lower half. So this implies that if we build a regression model that has the cover type, what used to be all just unexplained variance and residuals, errors, is actually going to be partially explained by the type of the book cover. So yeah, paperback's generally way less than a hardcover after controlling for the book's volume. They don't have this extra dense piece of cardboard on them. Here's that same regression table, but I've added one more line to it, which is the type of cover. So this cover colon paperback. So before we just had these two lines, and they haven't changed too much, but we have this third line and a coefficient that is negative and quite a small p-value for that one. So this negative estimate is telling us that when the cover is a paperback, our expectation is less. In fact, our expectation is 184 grams less than for a hardcover book, all else being the same. So I mentioned the interpretation of that this estimate for cover paperback. Do you remember what it was? And can you answer this question here? What is the so-called reference level? The reference level is like your base level. If you're talking about a clinical trial, it is your control group or your placebo group. If it is a I don't know, if you're talking about sex, it would be male or female, and it would be arbitrary which one is your reference group. Here we have two categories, paperback and hardcover. Which one is our reference group?
Paperback?
Actually, it's hardcover. Reference group is the one that the intercept corresponds to. So what this is saying is if you have a hardcover book, you only need to use these two coefficients to estimate the weight of the book. And if you have a soft cover, you need to make this fraction of minus 184 grams to it. So the reference group is the one for which there are the least coefficients. In this case, hardcover, there's no coefficient for hardcover. The comparison group is paperback, and it's a correction to the reference group. This regression could be done equally well with making paperback as the reference group, and then what you would see is here a cover colon HC for hardcover instead. Anyone want to take a guess of what the estimate would be if paperback were the reference group and we had instead a coefficient for hardcover? I'm just going to circle this as the correct answer. what would the coefficient be if we changed reference groups? Right now it's minus 184.0473. What would change? We switched reference groups. So our reference group now is paperback,
0.
and this coefficient tells us the correction that we have to make if it's a hardcover book. What things in this table are going to change?
How about if we think about it this way? That's predicting what the weight is going to be if it's a paperback, if it happens to be a paperback. How much you have to subtract if it's a paperback from the calculated value that you got from your regression. Now you're going to do the opposite. You're going to do the calculation for your regression, predict what the weight is going to be, but now you have to correct for it being a hardcover. So why don't you kind of go in the other direction now?
Okay, so yeah, in this case, the way we would use this table to calculate the volume of a book is if it's a hardcover book with 0 volume, it's just the intercept, 197. That's the weight of a 0 volume hardcover book. Maybe that's just the weight of the cover. Then assuming it has some non-zero volume, you multiply the volume by this and add it. And then finally, if it's a paperback book, you just subtract this amount from what you would have if it's a hardcover. So let's do it the other way now then, where paperback is the reference group. First of all, is the intercept going to change? Yeah, the intercept's going to change because then this part of the model will be the model for paperback books instead of for hardcovers. So this estimate is going to have to be smaller. And what's going to happen to this will be cover colon HC.
Positive value will be there.
Positive value. In fact, it's going to be plus 184.0473. So the intercept will be 197 minus 184. So the weight of a 0 cubic centimeter paperback book is 197 minus 184, which we could calculate this way. But if we switch reference groups, then that's just the intercept. So this is an important thing just to be aware of what your reference group is. And you can tell what your reference group is in your regression output by the one that is missing coefficients. The fact that there's no hardcover coefficient in here tells me that hardcover is the reference group. And if you have 5 different categories, like race, ethnicity, or something like that, the one that doesn't have a coefficient is your reference category. You'll see coefficients for all the others. Next, multiple choice. Which of the below correctly describes the roles of variables in this regression model? Well, first, tell me just what's the response variable here?
Weight.
Weight. Okay, so we can get rid of C. Okay, the explanatory variables. Let's see, volume, yes, and let's see, paperback cover or cover type. We could kind of say either of these. I mean, this coefficient is a coefficient for paperback covers. This is what we call a dummy variable. It's a variable where it's 0 if it's a hardcover book and it's 1 if it's a paperback book. So this is a dummy variable for cover type, and it's one where it's equal to 1 if it's a paperback cover. So I think both of these are kind of right, and I suspect that this is the intended answer. But they're both right. Okay, just so you have this in writing, I made you do it all without writing any of it down first, but how do you make predictions from a multiple regression model? So the predicted weight with that hat over it is the intercept plus the slope times the volume, 0.72 times the volume, minus 184.05 times this dummy variable called cover colon PB. So this dummy variable cover colon PB is 0 for hardcovers and 1 for paperback books. So your volume is a numeric variable, and this dummy variable for the binary variable cover type is also numeric, and this gives you actual numbers that you can plug into a formula to calculate your predictions. And the fact that all of these add to your weight makes this what is called an additive model. When you get into logistic regressions next semester, that is a multiplicative model, and you'll have to keep separate whether the models you're working with are additive or multiplicative. Here it's additive because every coefficient adds something or subtracts it from your prediction, whereas in a logistic regression, when you're talking about odds ratios, every coefficient will multiply your odds ratio by something. So just file that away for future. When you have your first class on logistic regression, you can ask whether it's an additive or a multiplicative model and get a head start on it. So, and for hardcover books, this dummy variable is 0. So you're going to plug in 0 and just use those first two coefficients. And for paperback books, the dummy variable is 1. So you have to subtract this coefficient of minus 184. Piece of cake. You can visualize this nicely by thinking of it as two separate lines. So we have this line for paperback and this line for hardcover. The line for hardcover has this intercept of 197. And then the slope is exactly the same for the paperback, but the intercept has that 184 subtracted from it. So you can see this looks like a better model for book weights than what we had without using cover type. We've been over all of this stuff, but just I guess to make sure it hits home, that intercept corresponds to the reference category, hardcover books, and it's the weight of a hardcover book with 0 volume. That's expected on average to weigh 190 grams. So maybe it's the weight of the hardcover. And then the slope for volume means that for everything else held constant, the cover type, only the cover type in this case held constant, that for 1 additional cubic centimeter of weight, it weighs 0.72 grams more. And this slope, or this coefficient for cover paperback, means that all else held constant for 2 books of the same volume, paperback books weigh about 184 grams less than hardcover books. So this is your interpretation for coefficients of any additive model. All right, one more of these multiple choices for you here. Which of the following is the correct calculation for the predicted weight of a paperback that is 600 cubic centimeters? All right, we we have to start with the slope 197. So we can get rid of that. Yeah.
That's 8.
A, so plus 0.72 times 600 minus 197 times 1 because it's a paperback. Yep, it is A. Thank you. All right, let's get on to another more public health example, modeling poverty. So this is a data set. Whoops. Dropped my mic here. A data set provided by the book where the response variable is the percentage of residents in a county living below the poverty line, with 4 different predictor variables. The percent of residents living in metropolitan areas, percent who are self-reported as white, the percent who graduated from high school, and the percentage of households with female only head of household. With observations across all 50 US states and District of Columbia. So here they are. Sorry, it's not county level, it is state level. So we have 51 data points here in each of these scatter plots. This is an exploratory set of scatter plots called a pairs plot, where they have plotted just a scatter plot for each of the pairs of variables so that you can kind of quickly see where there's not much correlation and where there is a big correlation. So you can see there's a fairly big correlation between poverty and high school graduation with a negative correlation. So in areas with lower or with higher rates of high school graduation, there is less poverty because it's negatively correlated. And there's also a fairly strong correlation between the percentage of self-reported white and the percentage with a female-only head of household. So where there are more self-reported whites, there are fewer female-only heads of household. And also a pretty strong correlation between, anti-correlation between high school graduation and female heads of household. You can kind of see these in the plots what this minus 0.61 correlation looks like, what this, let's see, this minus 0.75 correlation looks like, and this minus 0.75 correlation looks like. Those are pretty strong correlations. So you can see it's a little complicated. It would be hard to say which, or what's causing what here, but these are correlations that exist in these different, 4 different predictor variables and our response variable of poverty. But we can probably predict that when we're trying to predict the percentage of households living below the poverty level, we're going to have a pretty strong negative coefficient for high school graduation. And it looks like a positive correlation for female heads of household. And the other 2, not as strong. Starting with a simple linear regression just for the percentage of female heads of household, we have a positive coefficient. And you'll notice it's not the same as the correlation. Remember the relationship between regression estimates and Pearson correlations. So that last page was showing Pearson correlations, and this was, let's see, poverty and female heads of household. This was 0.53, and here the estimate is 0.69. Do you remember what the relationship is? Anyone? The Pearson correlation is the regression coefficient if if you scale the variable to have a standard deviation of 1. So, so this is positive because the standard deviation is not 1. It was that R equals the beta regression coefficient over the standard deviation of the variable. So same sign, just different scaling. So, but there's a small p-value here. There's a statistically significant association between poverty and the percentage of female householders, and a positive relationship. So that was Pearson correlation, which was great, and R squared was great when we covered it last class for simple linear regression. You had this. I gave you, I think, 2 different ways to calculate R squareds. Well, in fact, there's 3 ways, and you're going to need a little bit more options for multiple regression today. So the first way is you can just square the correlation coefficient of x and y. Remember, that was the relationship, little r Pearson correlation. If you square it, you get the coefficient of determination. Alternatively, we didn't cover this one, but you can, if you just take your predictions for y and calculate the correlation between your predictions and your actual values, that gives you a Pearson correlation. You can square that and get your coefficient of determination R squared. That's kind of cool. And then there's the definition that the coefficient of determination is equal to the explained variability in y divided by the total variability in y. So we covered the first and the third ones of these last time. So why would you need 3 different ways to do this? Well, this third way is, in fact, the easiest way to do it for multiple regressions. And that's because we get all of the things that we need from an analysis of variance table. Here is an example just for the linear regression between poverty and female householders. The sum of squares total is given in the bottom row of your table, 480. Your sum of squares of the errors, 347. And your sum of squares of the model is this 132.57. And when you add these 2 up, you get your total. So you should always be able to, if you're looking at this sum of squares column, you add them up for each row of your ANOVA table to get the total sum of squares. And this gives us a way from the ANOVA table to calculate our R squared by taking this explained variability, the 132.57, divided by the total variability, 480, and that gives us our R squared. We take the square root of that 0.28, we should get, what did we have here? This 0.53. And we have that. That's easy to go between those because this is just a simple linear regression. How about when we get into multiple regression? You can't just use the correlation between x and y because you have multiple x's. And so that's one reason. You have multiple x's. You can't just calculate Pearson correlation. It's not defined. And there's a third thing that we're going to want to define something else called an adjusted R squared that'll be similar in definition to this last one. And it's something that will account for the fact that the more variables you have, the higher your R squared will get, whether or not those variables are actually adding anything to the model or not. Okay, so let's look at a multiple linear regression with female householders and self-reported number or fraction of whites. our linear model output, the regression output, gives you these coefficient estimates, these things you're getting kind of used to. And then the analysis of variance output doesn't give you any coefficients, but it gives you all of your degrees of freedom and sum of squares that we'll need for calculating coefficient of determination. So it's easy here. Our explained variability is just the sum of these two, 132 plus 8.21 divided by our total 480, we get an R squared of 0.29. So this is a nice way to calculate R squared for multiple regression. You'll find it's in your regression out, but also you don't have to do it manually, but it is easy to do manually from your NOVA table. One thing to be aware of that was never an issue with any of our bivariate methods, but becomes an issue with multivariate methods is collinearity. And this is where you have two or more predictor variables that are correlated to each other. So we saw back on those pairs scatter plots that percentage of female householders and percentage of whites were correlated to each other. That makes them somewhat collinear, and you see what you can see some strange behavior in your regression tables when you have collinear variables. So when we had only female householders in the model, we had an estimate of 0.69 and a standard error of 0.16. And when we add the white variable into it, we actually see an increase in the apparent effect of female householders on poverty, and also an increase in the standard error. This increase in the standard error is a sure sign of collinearity. And this is not too bad a case of collinearity, but when you have variables that are correlated with something like 0.9, you'll see a large increase in the standard error in your regression tables. And that increase in standard error you can think of as telling you that you can no longer estimate either of these coefficients very well because they're so correlated to each other. If female householders and percentage of whites are highly correlated, then you can't really say what the contribution of one is while holding the other one constant. Your uncertainty in being able to do that increases the more highly collinear they are. And in fact, we're not going to get into this, but there is a measure you can get that is called the variance inflation factor. That's a measure of collinearity, and it says that it is the amount by which your standard error inflates due to collinearity. So, simple enough definition, we call two predictor variables collinear if they're correlated. The only reason there's another word besides correlated is because it's in this context that they're both predictors in a multivariate model. So when you have correlated variables that are both predictors in a multivariate model, then we call them collinearity. Ideally, we also call these independent variables. So ideally, they would be independent of each other. And when they are independent of each other, when you add one variable, it doesn't change the other estimates. It doesn't change the other estimates, and it doesn't change their standard errors. That happens when they're collinear. It's not ideal having collinear variables in a multivariate regression because you can't separate their intertwined effects. And if you were designing an experiment, you would design it in a way that you control the independent variables independently. But when you have an observational study, you don't necessarily have that luxury. Some of the predictors that you're observing are collinear, and you're either going to have to make a decision to not consider one of them, or you might still want to consider it, but keeping in mind your interpretation of the model in terms of causal inference and which one you expect to be the causal variable, etc. But it both complicates model estimation and it complicates your model interpretation. So it's something that you need to be aware of. So, and as I mentioned, you can't necessarily avoid collinearity in observational data sets. So one problem that comes into this multiple R² value is that anytime you add another variable, that sum of squares column, that's always greater than 0, right? So adding any variable, even a completely random variable that has nothing to do with your outcome, it will always increase R², because adding any predictor variable when you fit a model to it will give you some amount of prediction. It's sum of squares of the different possible predictions for that variable has to be greater than 0. So the more variables you add, the higher your R² gets. But there's this alternative, the adjusted R², that has this nice property that if you add a random variable with no association to the outcome, it does not increase, it just stays constant. So it's an adjustment, sort of a penalty for adding variables that makes it so that if you add a useless variable, nothing changes. And it just differs from the regular R² by this additional factor of n-1 over n-p-1, where n is your number of observations and p is the number of predictors. So the more predictors that you have in here, the more it penalizes this sum of squares. So whereas without this, your sum of squares of errors will always go down as you add variables. That is offset by this increasing denominator, the adjusted R². It's always smaller than R² because p, your number of predictors, is going to be 1 or more. It's a penalty to the number of predictors, and it gives you something that you can use for model selection. So if you're trying to build a predictive model or your best multivariate model, you can just choose the model with the highest adjusted R². Example of calculating it. So for this this last example, we had before the 339 are the sum of squares of errors. 480 was the sum of squares of total. We have 51 observations for 50 states plus District of Columbia, and we have 2 predictors here, the female house and white. So the correction here is quite small, 50 over 48, and this value is quite close to what we had. But the more different independent variables you add, the greater the difference comes between R² and the adjusted R². So just to wrap up, multiple linear regression is an additive model. You'll get next semester into logistic regression, log linear models that are multi-linear models. Also, log linear I think won't be until fall of next year in BIOS 2. It's also Cox proportional hazards models. Those are multiplicative. Collinearity, you can recognize it by an increasing standard error of your coefficients as you add collinear variables into the model, and it makes them less interpretable because your predictors are not independent of each other. And you can use both R-squared and adjusted R-squared. They are increasingly different as you add more predictors into your model, and the adjusted R-squared helps account for the fact that random predictors will increase your R-squared, and it makes it stay constant as you add useless predictors. This is just a nice summary table that your text had of different tests depending on your type of independent variables and your goals, and something that might be just useful as a little reference, possibly for your project, but in general for knowing about different possible types of tests. And it has, so for example, this is what we what we focus most of our time on with a continuous, normally distributed independent variables, describe one group using its mean and standard deviation, compare one group to a hypothetical value, one sample t-test. But this table is nice. It also gives these alternatives for non-normally distributed population. So in cases where that assumption of the normally distributed response variable doesn't hold, you have these alternatives. These are called rank tests or non-parametric hypothesis tests. So for a one sample t-test, if you have obviously non-normally distributed variable, you can consider this alternative Wilcox and rank sum test, for example. And then there's another column here for categorical variables, most of which we covered in this course, not quite all of them. So that is all we have for the lectures for this semester. You should have all gotten an email about teaching evaluation forms. Please do fill those out. They're important for both of us and for the school. And I would just like to thank you all for coming into class and participating throughout. We'll have our lab session tonight, and then next class will be the final projects. I will spend tomorrow morning taking another look at all of the preliminary stuff that you have handed in and do my best at giving you some useful feedback. But I have ordered display boards and thumbtacks for us to use next week. I think what we will do is just do them one at a time, set up on this table here. I got 6 of them, so several people can go ahead and tack their papers onto a board, but then one at a time you'll come up here and present it to the class. You'll have about 5 minutes to present your project to the class just by pointing at the board. So keep in mind as you print things out and it sits here, it should be visible to people who are we'll move chairs out of the way and so everyone can just stand. We'll see how and it's been so long since we had 25 people in here that we'll have to see how it
Probably
works.
make like a circle or something like that.
Maybe a circle, something like that. So try to make your figures and your text such that people will be able to read them, and you'll be able to stand by them here and point at things and just explain your project and your findings.
Sheets of paper, like standard size sheets of
Could
paper.
always use the hall.
We could use
Most of sessions wind up at halls.
could use the hall. We don't have, I didn't get easels though. We just have
You know,
these trifold
it just occurred, as you were
things.
saying that, it just occurred to me that all the resources that we had before now all dried up. In other words,
Yeah.
we had that room with all the materials and the easels and that.
Yeah, I could have gotten the easels, but I was thinking about the room and assuming, well, if it's here, this trifold board will work work just fine. So number of sheets of paper, I mean, that is up to you. My suggestion of no more than 10 was just what should be, you know, manageable to get through in a presentation. But these trifold boards are big. They're like 36 inches tall by 48 inches wide. So, I mean, you could put tons on there if you wanted to. And it is better to have more sheets of paper than to have too small writing. But for the amount of time you have, having a sufficiently large font and 10 sheets is probably about as much as you can get through in a short poster presentation. But yeah, you have a 36-inch by 48-inch. It's a trifold display board with a big section in the middle and a couple short sections on the side, and you can set it up the way you want. We'll have a bunch of thumbtacks for you to post things onto it. And remember, there will be prizes. Tony and I will have a grading sheet corresponding to the rubric that I think you've seen, and we will be sitting there grading as you make your presentations. Any questions before we take a break and move on to lab?